Well, welcome everyone. My name is Kurtis Bowman, and I am your moderator for this session. I'm very pleased to be joined by Sandeep Dattaprasad from Astera Labs and Steve Scargall from MemVerge. We're going to talk to you today about how we believe CXL can be used to improve performance as well as functionality of AI and HPC applications. I've already done the introduction. Gentlemen, do you want to introduce yourself a little bit more?
Sure, absolutely. Thank you, Kurtis. Hello, everyone. Thanks for joining us today. My name is Sandeep. As Kurtis mentioned, I'm part of the product management team at Astera Labs, and I'm responsible for Astera Labs CXL memory controller product line.
Yeah, thanks very much. Yeah, so I'm Steve Scargall. I'm the product manager and software architect at MemVerge. So I spend a lot of my time, most all my time, working on our CXL line of products, so memory tiering, sharing, and some of the other things that we'll get into today as well. So,
all right, let's go to the next slide. So just a quick intro to CXL. It is an industry standard that's been evolving since about 2019. And it is set up really to be something that allows you to connect multiple types of devices on an as-needed basis. And so, some people call it pay-as-you-grow, other people give it different names, but it's that composable infrastructure that allows you to bring in the types of devices you need for your system and its performance. One of the key pieces is it's backwards compatible. Key there is it is something that allows you to save your investment. So if you invest in an early version of a CXL device, it continues to work as you upgrade your network and your systems. And because it is composable, it tends to lower overall cost. You don't have to buy more and more and more servers every time you want to expand a particular entity. You can buy just that piece. So if you need more memory, you can buy just more memory and improve your performance because you get more bandwidth and more capacity as you do that. Also, in order to be a good standard, you have to have a compliance program. And so CXL has put together a compliance program. If you go out on the website, you'll actually find what we call an integrators list of the people that have passed that testing to make sure that they can be compliant and interoperable with the other devices. And finally, something to point out is it's not just a spec anymore. CXL devices are out in the market by multiple companies. You can deploy them into your infrastructure today. The next slide goes over kind of how we came out with the specification. So if you go all the way back to 2019 with our first specification, it was a point-to-point interconnect. It had a set of devices we called type 1, type 2, type 3 devices, but it was really intended to be inside the box. With 2.0, we added switching capabilities, still though local to the box. Those are the devices that are out in the market today. With 3.0 and 3.1, we actually started to add a fabric piece to the specification. So it really allowed for multi-layer switching, talking from multiple devices to other multiple devices, brought in the sharing capabilities. But because now we were going outside the box, we also needed to do things like bring in a fabric manager to talk to about what devices can talk to what other devices. We also had to bring in security. So we brought in what we call the TSP, or the Trusted Environment Security Protocol. So a lot of things came in to allow for a fabric to be developed around CXL. And that's really the big changes as you think through it. And you can imagine those 3.0, 3.1 devices taking a few years after the spec is available. So imagine those out in the 25 timeframe for, again, putting into your infrastructure. So with that, that's just the brief overview. I now turn it over to our experts. And the next slide is a great slide for them to really talk about what is CXL, how does it get used? And I'll hand it over to Sandeep. Why don't you tell us a little bit about how you see CXL being used with AI and HPC?
Yeah, thank you, Curtis. Yeah, that is an interesting topic, isn't it? Because considering the level of traction we've had in the industry, particularly related to generative AI, such as ChatGPT, we need to be paying close attention to what can we develop today with the newer protocols such as CXL 3.1, and how does it aid in generative AI and HPC. So we're talking about generative AI. The first part is the training part, which requires significant bandwidth, which is often met by GPUs to ensure large amounts of data are processed. The second part is more interesting, which is the inferencing portion, where the trained language models such as ChatGPT would rely on augmented generation. For LLMs, you need an AI framework that enables use of additional data sets to improve accuracy, because when you are typing in a query into ChatGPT, you really need accurate results to be showing up. And for that, you need to store high dimensional data such as images and text and so on and so forth, so that the query would return the necessary result. And this is where CXL comes into play. And to more to that point, here we are showing memory expansion through single host as well as multi-host topology. In either of those cases, what you're really enabling is expansion of memory to generative AI types of use cases. Multi-port memory expanders are a lot more applicable for, obviously, when you have multiple hosts and if you want fabric managed capability. And this is where CXL protocol comes into play, wherein it has added a host of fabric management capabilities, FM APIs that are going to aid us in developing the entire fabric. Also, to add a little more on the TCO side, today HBMs generally use, GPUs generally use HBMs to increase the bandwidth and lower the power consumption for AI applications. However, it's extremely expensive. So one alternative and a plausible solution is you can use CXL, which would expand the GPU capacity beyond the limits of HBM and address what's called as memory wall problem, where you don't have sufficient memory to efficiently use processing capabilities of attached processor. So essentially, you're expanding the capacity as well as the speed of data transfers significantly, because otherwise you will not be using the hardware compute capabilities efficiently. And this is effectively what the today's solution provides. In fact, we have our Leo Smart Memory Controller through Astera Lab, which demonstrates how you can overcome the memory wall problem in AI. We can talk a little more about HPC in a minute, which is where the second block diagram with multi-level switching comes into play. Maybe to that end, Steve, would you like to expand a little more on the AI use cases that we can target with CXL 3.1 capabilities?
Yeah, absolutely. So I guess before I get there, maybe just expand on what Kurt said earlier. This is more than a spec, right? So for quite a while now, the Linux kernels had CXL support. So as you were explaining in the previous slide, right, we started with CXL 1.1 back in the 5.16 kernel. And now, at least at the time we're recording this, the 6.9 kernel is almost ready to be released. And through that evolution, we've gone through adding the CXL 1.1, 1.0, 1.1, 2.0, and we've also got 3.0 and part of the 3.1 spec being integrated as well. So as far as operating system support goes, at least from the Linux side, we can cover most of these topologies and use cases. Which is good news for us as software guys, because that allows us to begin working on the next generation of software, so that when the hardware lands, we're all ready and prepared, and we're not trying to catch up. And the way we do that is, yes, the kernel has support for CXL, but unless you actually have access to hardware, it's very challenging. So the other piece of the puzzle here is that QEMU, the virtualization engine, also has some of the key features of CXL. So we have memory expansion, we have DCD, the dynamic capacity device. We've just been pushing up some patches for multi-headed devices. We can do memory sharing and others. So whilst it's not hardware performant, it is at least functional for the software developers out there. So that, again, that's been a great advancement for us. So And then as we go to the right picture there, you know, fabric management, how do we do that? And again, you know, QMU has been helping us develop fabric management software. So there's some software out there from Liquid and Jackrabbits that's open source their solution, and the vendors will probably have, you know, proprietary APIs for their switches and endpoint devices and this, that, and the other. So the ecosystem is coming together and giving us all the tools that we need to build on top of our final solutions, and that includes the AI side. So I like what you were saying earlier, Sandeep. You know, the data throughput is key, right? I mean, we don't show GPUs in this picture, but you can definitely imagine GPUs either connected into the hosts or be in a separate GPU cluster. And then how do we get data into those devices, right? I mean, that's the key here. Is traditionally data has to come in over traditional storage protocols, right, which are inherently slow, probably over the network. Now, as we move over to a fabric network, we significantly reduce the latency and vastly improve the bandwidth and capabilities of that. So if my data from my AI model, whether it be training or inference, is sitting out there in a memory fabric, now I have the opportunity of reconfiguring that fabric and moving my data to where it needs to be. So if I need to train first, then I can provision my topology such that my data is pointing at my GPU clusters, and I can go train my model. Once it's trained, I can then move the results, the trained model, and move that over to some other environment where I can then start to do inferencing on that, right? So now we can start moving data closer to compute and where it's needed without having to do massive data copies of you know, how we do things today. So and we demonstrated some of this at the NVIDIA GTC conference, just a local data with a local GPU, but showing the clear benefit of CXL and being able to feed that beast, the GPU, with data faster than you can do traditionally if your data set spills over from the relatively low memory capacity of GPUs today. So yeah, we were able to show that data was available in DRAM, and then, you know, the data set was larger than DRAM, so it then spilled over to CXL. But we were able to achieve a 95% utilization of GPUs, which, you know, is the most expensive resource in this type of environment, right? So making sure they're fully utilized or better utilized than what you can do today gives you also better time to result or better time to insight. So not only are you getting better TCO on the hardware that you've purchased, but you can also either do more users, if that's data scientists, researchers, etc., on the hardware that you have available, and you know, getting the results faster. So
yeah, thank you, Steve. That's a very good point. Fabric management capabilities, having the software infrastructure to enable that was extremely important, and I'm really happy to hear that with CXL 3.0 and its capabilities, or 3.1 to be more specific, we are able to get there. But I do want to expand a little more on HPC side of it, in the sense that when it comes to HPC, it's basically a collection of separate servers called nodes, which are connected via fast interconnect. Obviously, there are different types of nodes depending on the task that you want to accomplish. But essentially, what it comes down to is for HPC workloads, you need a mixture of accelerators, GPUs, TPUs, FPGAs, so on and so forth. And I bring that up because what you mentioned earlier about composability, which is enabled by 3.1, is extremely important to enable HPC use cases. If you want to accomplish having systems with disaggregated resources, then you need to have protocols like CXL that enables it. And for clusters and data centers where modular expansion is essential as we grow the infrastructure, CXL 3.1 becomes imperative. So yeah, it's very interesting to see the ecosystem develop along with the protocol.
I agree. So great thoughts there, guys. Now, do you see a big difference in the usage models for either hardware or software as we look at AI versus HPC?
So in my opinion, there is a little bit of overlap and a little bit of difference. The overlap is really on the hardware side of things. In other words, the kind of hardware infrastructure or resources that you target would be somewhat common between AI and HPC. In other words, whether you are trying to accomplish composability via various hardware components being part of the system, or having a homogeneous system, your objective would still be expansion of resources, memory, bandwidth, so on and so forth. So that's where the overlap or commonality is. The differences between AI and HPC use cases would be the application, upper level application that would use these hardware resources. Maybe to that end, Steve, you can add a little more on how it differs on that level.
Yeah, and I think I would go back to the where's my data type of thing, right? I mean, HPC is typically an MPI type of interface where I'm trying to send a lot of messages around my network across the hundreds or thousands of nodes. And I think in the 3.0, 3.1 timeframe, when I've got memory appliances and my data is available to all nodes at all times using byte addressability, I would probably see a future where we would have the applications access the data in place versus having to copy it locally, process it, and then send some result back out to some other node. So yeah, I think that's the way that I would go with this type of solution here. So and how we access that, I mean, clearly the applications need to be aware that they're running in this type of environment, right? So go away from the traditional local resources and more into a fabric-centric view, again, where my data is accessible, byte addressable versus block addressable, or sending some large packets over the wire, right? And again, there's some great research and solutions in this space. I mean, there's a couple of file systems that are currently being developed that are fabric aware. So rather than using something like NFS or Gluster or anything like that, then a CXL fabric file system has significant advantages here. So allowing you to keep your application either unmodified or make some slight modifications to it, but still being able to access that data. And I think for the AI side, again, it's more of, am I doing the inference? Am I doing the training? Which piece of the puzzle am I doing? And what resources do I need? So going back to the composability thing, and from an infrastructure person, how do I get the best utilization out of this environment for us? So yeah, I think software's got a long way to go, but it's definitely getting there pretty quickly, and I think it'll definitely be ready by the time we get hardware to market here in the next year or so.
Excellent. So what I'm hearing is not only will you see a performance increase because you're not moving that data around, but you're actually see a power reduction because you're not moving all that data everywhere, and you're spending more time in your compute cycles.
Yeah, no, exactly. I mean, power and data center cooling and everything else is a big factor for sustainability reasons, right? And yeah, I definitely see the topology more on the right-hand side, right, as we get into the big fabrics being a great beneficial solution to that end.
So, all right. Any other comments on this slide, or should we go into the security piece?
We can move into the security piece.
Yeah.
All right. So go ahead, Sandeep.
Oh, sorry. I was just going to say security is an important aspect of it, isn't it? As we move towards expansion of our AI infrastructure, it behooves us to ensure we have all the industry standard security protocols to be implemented, particularly related to cloud service providers, as well as enterprise customers for that matter. So yeah, there are a lot of things in CXL 3.1 that are defined related to security that we can talk about here.
And Steve, oh, go ahead. I was going to ask Steve on the software side of the house. How do you see TSP or trusted execution environments meshing with the efforts in the OSs?
Yeah, I mean, obviously the effort to enable this type of feature in the hardware and software is key, right? And we definitely don't want data leaks, data breaches, or one VM accessing data from another VM, right? So this is going to be absolutely critical for the future environments. Particularly as you do the composability, and let's say you've got some Kubernetes environment out there where you don't really know what pod is going to be run where. You definitely don't want a pod to exit either cleanly and then somebody come along and access the same memory and gain access to data they shouldn't do. And the same is true for VMs. So, from a kernel perspective, all that stuff's being put in place here. The same for the virtualization technology, again, like QEMU. All of that stuff's either there or being put in place very shortly to allow us to get that isolation that we need in these sort of big environments. So.
Yeah, you hit the nail on the head with your virtualization comment there, Steve, because even with CXL 2.0, we do have a certain level of security because it provides integrity and data encryption, also known as IDE, which is prevalent in the industry. And with that, traffic across root complex switches and devices at link layer would be protected. And that is the center part of this block diagram. The question now is, how do you ensure end-to-end protection? And this is where the security enhancement in CXL 3.1 comes into play. And if you think about it, from the data center perspective, what you need is you need protection of data at rest, data in flight, and data in use. And you talked about virtual environment. That is also extremely key because as you move towards more and more cloud service provider kind of applications, virtual environments are going to become extremely important to secure. And also you need to confirm the identity of the device itself. And this is where the attestation piece of it comes into play. So what CXL 3.1 did was it implemented the Trusted Security Protocol, also known as TSP, for handling security at a platform level instead of just at a device level. And what I mean by that is CSPs would have multi-tenant VMs, right, sharing devices that are connected via CXL. And they will need that end-to-end security that I was referring to, including virtual environments. And as a result, things like confidential computing, which is becoming extremely important and is a hot topic in today's cloud VMs, need to extend past the confines of the server to all the devices that are attached to the fabric. With 3.1 TSP, we can enable confidential computing, particularly targeting workloads and virtualization-based trusted execution environment. And this is exactly what this block diagram shows. You have the TEE virtual manager, which is TVM in this block diagram, which is separate from the VMs that are traditionally part of CSP's infrastructure. And all the things that I mentioned earlier about protection of data at rest, data in flight, data in use can be accomplished if you look at this block diagram. And if I were to describe a little more about that, you can enable encryption of the sensitive data at rest in both host and device memory, which is the two ends of the pieces that you see in the block diagram. Obviously, IDE would be the centerpiece as enabled by 2.0, and that carries over to 3.1. And now you can control and define the security features, enable them as required, lock the configuration, because all this is enabled in 3.1. And last but not least, confirming the device identity. Are you talking to the right device? And that you can accomplish even before your VMs and the operating system kicks in. And that is what you accomplish through attestation measurements, attestation as well as authentication measurements, such as secure boot. And this is where all the capabilities that 3.1.
I've got to cut us off. We're at time.
Sure.
But I do want to thank you and Steve both for your insight. And as we look at the future of compute, CXL looks like it's got a real strong place in AI and HPC environments. So thank you again.
Thank you.
Thank you.